Ladies and gentlemen, welcome to our November's webinar, adding to the free session of the first part of the Groundwater World Congress, a joint achievement of EIH, Al-Sud, and ABAS. We started with 8 panel sessions in September, where we reached more than 10,000 views. Should you miss it then, please access our ABA channel on YouTube. All the presentations are available at any moment you want to see. You remind you that we will offer 2 panel sessions per month until August 2021, when we will host the presential part of our event, if COVID situations allow us, but I hope yes. One panel more market related and the other more scientific, as this one that we will have this morning in Brazil, this afternoon in Europe and other parts. Scientific panel. Please follow ABAS on social media to stay informed about news about the Congress, or EIH and Al-Sud social medias, websites, and whatever. We have 900 participants of our thematic, 10 WhatsApp group. There is some interesting discussion group. And our app has been downloaded by more than 400 participants. These always growing numbers are a proof of the successful digital strategy to create the largest groundwater community in the world. We would like to thank our sponsors, supporters, and expositors who allowed this great event to take place in Brazil. Our main sponsor is ANA, Agência Nacional de Águas e Saneamento Brasil, the National Water Agency. We would like to thank for the support of the Committee da Bacia Hidrográfica do Rio São Francisco, AGB Peixe Vivo. Also our exhibitors, Altri, Bodega do Poço, Chicago Pneumatic, Ebara, Elgi, Maxi Água, the Groundwater Project, CRI Bombas, Lepono, Aragon Sondagens, Clean Environment, Franklin Electric, Pase Hidrometria, Perfuratrizes DTH, AGB Peixe Vivo, ALS, Bryant, Eurofins, G-Hidro Monitoramento, GLP Laboratórios, Exis, In Situ do Brasil, PRD, Rigs, Trionic, Vapor Solution, Water Service and Technologies. Today we will have 3 short presentations, followed by a roundtable where the viewers can participate by sending questions to the speakers. The questions may be sent by our app. Please download it at your preferred app store. Just search for IEH 2021 or directly on YouTube channel. This session has simultaneous translations into Portuguese, also on YouTube. Please make sure you direct your question to one of your guests. The session will be hosted by me, Didier Gastmans. I'm a researcher at São Paulo State University, and our guest speakers are Professor Dr. Seifu Kebede Gurmessa. He is a Sub-Saharan Africa Vice President of IEH. Mr. Bryant Jurgens is a research hydrologist of the US Geological Survey, and Professor Dr. Zheng-Tian, he is Professor of Physics and Dean of the School of the Gifted Young at the University of Science and Technology of China. Now, I will introduce our first speaker, Professor Dr. Seifu Kebede Gurmessa, Sub-Saharan Africa Vice President of International Association of Hydrologists. The theme of his presentation is Isotope Hydrology Applications in Uncovering the Hidden Groundwater Resource in Africa. Seifu is a hydrologist by training, with a specialty in tracer hydrology and geochemistry, especially on water quality. And he obtains his PhD from the University of Avignon in France in 2005. And he has served at Addis Ababa University as Associate Professor of Hydrogeology. And he joined the University of KwaZulu-Natal as Associate Professor of Hydrology in last September. He authored more than 50 peer-reviewed papers and 1 book. He is the Sub-Saharan Africa Vice President for the International Association of Hydrology, and he co-chaired the Water Quality Commission of this EIH. Thank you, Professor Seifu, for accept this invitation. And your turn, please.
Thank you, Didier, for the invitation and the introduction. My name is Seifu Kebede, Gurmessa. I'm based at the University of KwaZulu-Natal, South Africa currently, and I'm Vice President for the International Association of Hydrogeologists, Sub-Saharan Africa region. Didier asked me to present the stable isotopes, or how stable isotopes have been used in Africa to understand the groundwater resources in this part of the world. And my talk will be mostly around stable isotopes of water, oxygen-18, deuterium, and some touch on tritium and other tracers like CFCs very briefly. So in Africa, groundwater is the main source of drinking water. And it is expected that groundwater is going to play a significant role in socioeconomic transformation in Africa, poverty reduction, food security, industries, and etc. And this map is from the British Geological Survey showing aquifer productivity of Africa, regardless of the fact that most part of Africa is drier, particularly the northern part of Africa is drier. Some of the biggest aquifers are also located in Africa. And this map shows, the two maps shows the previous isotope hydrology projects in the region, mostly led by bilateral collaboration between IAEA, the International Atomic Energy Agency, and African member states. As you can see in the figure in the right, there are a number of studies, groundwater studies, using stable isotopes of water, tritium, carbon-14, and other chemical traces. And the figure you see in the right is the map of the global network in isotope in precipitation, and the GNIP stations, and some of the GNIP station dates back to 1961. For instance, this one in Addis has been established in 1961, and has been serving as a basis for interpreting the isotopic compositions, oxygen-18 deuterium compositions of groundwaters and other meteoric waters in the region. You know, stable isotopes have some good special characteristics. You know, during the hydrologic cycle, when water moves from one environment to the other, you know, and whenever there is change in phase of the water from one form to other, from liquid to vapor, from vapor to liquid, and etc., there is a commensurate or an accompanying change in isotopic compositions. Isotope ratios also change. And this process called isotope fractionation leads to a spatial and temporal difference in the oxygen-18 and deuterium isotopic compositions of natural waters. And fortunately, once a water is imprinted with these isotopes, the compositions will remain the same unless otherwise there is a phase change. So this means that isotopes can serve as a tool to trace water movement in the environment. And one of the earliest studies back in 1960s, early 1960s, late 1950s, is by Craig, who collected water from across the world and then plotted oxygen-18 content against deuterium and got this line called, by that time, the Craig line, and nowadays called the global meteoric water line. And one of the observations that has been made there is that there are some waters which really depart from this line, best fit line called the global meteoric water line. Some waters in closed environments and evaporated water bodies depart from this line. And then the theory of kinetic fractionation came after this observation. You know, prior to this time, isotope fractionation has been considered as equilibrium process, whereby coexisting phase exchanges isotopes on equilibrium basis, but kinetic fractionation is also an important process. And then the Craig-Gordon 1965 model came after this observation. And then this plot, the oxygen-18 delta deuterium plot, serves as a basis for a rapid interpretation of isotopic compositions of natural waters. Any departure from this line of waters that one collects from a catchment, from a basin, any departure from this line has a hydrologic reason, certain hydrologic reason. And then these hydrologic processes or hydrologic reasons can be quantified. For instance, evaporated lakes or open water bodies plot along this line called the local evaporation line. And then the farthest the water plot away from the global meteoric water line, it is an indication that the degree of evaporative water loss compared to its inflow is higher as you go higher in this, on this line, the local evaporation line. And then waters which undergo geothermal exchange at high temperature plot on horizontal line called the positive oxygen shift. And then other waters, depending on the processes, chemical and physical processes, plot elsewhere. And then this serves as a basis of interpreting isotopic compositions of groundwaters and other meteoric waters. So one of the things that the isotopes have revealed about groundwaters in Africa is determining the origin of large groundwater bodies. As I've mentioned earlier, Africa is underlain by, in some places, really huge, big aquifers in arid, some of them are in very arid environments, in deserts, like the Nubian sandstone system you see here, the northwestern Saharan aquifer system there, the Illumiden aquifer in Central Africa around here, the Senegal basin, the Stamperit, the Karoo, and then several large continental scale aquifers underlie Africa. And the question is, given that the recharge amount is very low nowadays, the recharge numbers are very low, less than 5 millimeters in some cases, and near zero in most cases. And then what is the origin of these groundwaters, deep, sometimes fresh groundwaters you get in northern part of Africa and elsewhere? So earliest isotope hydrology studies revealed that these waters underlying the vast area in Africa have some unique oxygen-18 and deuterium isotopic content. So these are the plots you see in boxes here are taken from different countries. This one, for instance, for Algeria, Libya, and then Sudan, etc. If you see the oxygen-18 deuterium content of these waters, most of these waters in groundwaters are highly depleted. And compared to the present day recharge, their isotopic characteristics is really different, very, very different. And then these kind of waters cannot be related directly to the present day rainfall. And then the interpretation was that these waters must be recharged under a different climate condition from the present day in the past. And how old cannot be directly determined from the oxygen-18 deuterium compositions, but from carbon-14 and other tracers can tell the age of these waters. Okay? And it is later determined that these waters are, some of them are Pleistocene waters and others are from Holocene, mid-Holocene and early Holocene phases. And this is an example of a study of that sort of aquifers in Sudan, showing 3 distinct characteristics: paleo waters, paleo groundwaters, old groundwaters, and modern waters, modern groundwaters getting their recharge from the Nile, and mixture between these 2 types of groundwaters. So the isotopes served here as to identify paleo waters, the mixed waters, and the modern waters. And then another nice way of plotting this is has been done by Jasheko 2019, showing the delta 18 oxygen content of the Pleistocene waters, the old waters, versus delta oxygen 18 of Holocene waters in the same environment. And that difference is what is shown in this figure here. And then you can see on the plots also that, for instance, during the Pleistocene times, what is on horizontal axis is carbon-14 concentration, and vertical axis is oxygen-18. So during the Pleistocene times, the waters of that recharged during that time are highly depleted, and then, sorry, it is the reverse. So the younger waters are these ones, higher percent modern carbon. So the older waters are highly depleted. Older waters are depleted, the younger waters are enriched in their isotopic content. So this reveals that the vast continental scale aquifers underlying Africa, Northern Africa, have their origin from the Paleo recharge during Pleistocene wet phases and early Holocene wet phases. And so that is one of the major contributions of isotopes in understanding aquifers in Africa. The other application is recharge rate and recharge mechanism, determination of how much of the rainfall gets into the aquifer, and then in what way that this recharge water reaches the water table, the mechanism of recharge. So I have 3 slides here. First, on the recharge rate. So one of the use of isotopes in determining recharge rate is in arid environments, vadose zone soil moisture profile, chloride profile, and tritium profile. These two are directly linked to the chloride concentration, for instance, is linked to recharge rate. And then the chloride profile accompanied by the tritium profile, which indicates the age and the moisture content, this can be converted into recharge rate. And stable isotopes of water, although they don't directly tell us the age of the water, but they tell us, the processes. Okay, are the processes really related to recharge, or there are other processes that control, for instance, the variation of chloride and tritium in the subsurface. And there are a number of, or a handful of studies in Botswana, Namibia, Sudan, Egypt, Libya, and Senegal, Niger. And then these profiles, soil moisture profiles, reveal that the recharge rate is in the order of less than 1 millimeter per year to up to 20 millimeters per year. And this has been tried in many other places as well in Africa. And then the other way of using tracers, not specifically the stable isotopes of water, is in looking into the profile in the saturated zone, concentration of tracers like CFCs and SF6 in saturated zone, and based on the residence time and the thickness of the unsaturated zone and the porosity considerations, one can convert this CFC and SF6 profiles in saturated zone into recharge amount. This paper by Banks is published actually early this week. And then the study has been conducted in Ethiopia, Uganda, and Malawi, and shows that the recharge rate varies anywhere between 20 to 70 millimeters for Ethiopia, 40 to 100 millimeters for Uganda, and 30 to 70 millimeters for Malawi. Actually, this region of Africa is more wet compared to the region where the unsaturated zone profile has been taken, like Senegal, Sudan, and etc. So both saturated zone and unsaturated zone applications of tracers, use of tracers has been used in Africa to reveal recharge rates. And the other application actually is recharge mechanism. And there is some unique features of groundwater recharge in Africa. So these isotopes reveal that recharge is taking place preferentially from heavy rainfall. So for instance, if you see this figure here at the lower corner here by Darling and Gazau, also the figures were drawn for something else, you see that the weighted mean rainfall composition, which is a dot here, and the groundwater composition, which is inside this envelope, plot in 2 different corners of the global meteoric water line. And then this tells that the groundwaters come from the most depleted end of the rainfall, which means heavy rainfalls, which are often depleted in their oxygen 18 and deuterium, recharge the aquifer. So the story is the same in Zimbabwe, it is the same in Tanzania, etc. If you look Uganda, the rainfall, mean rainfall plots, the groundwater plots around the mean rainfall, diffuse recharge is more important. So by just comparing oxygen 18 in rainfall and groundwater in an environment, one can have an idea about the recharge mechanism. And then extensive studies and data compilation by Jasheko and Richard Taylor revealed that in Africa and tropical regions mostly, recharge from rainfall is biased towards the heavy rains. Heavy intensive rainfalls contribute to the groundwater recharge. So in the perspective, in the future, with climate change and etc., there are some assumptions or speculations that in the future, because of increase in rainfall intensities, groundwater recharge may also increase in this part of the world. This is just speculations, and then could happen in the future. So the other application is determining source of groundwaters. Where is the groundwater coming from? In mountainous environments like this in the Horn of Africa, East African regions, we have adjoining valleys. So you have the mountains and the valleys. So the question is, where is the groundwater in the valley coming from? So this is taken from Berishani 2018, not for East Africa, but for, I think, drawn for the US. So in the valley environment, the groundwater can come from multiple sources, from local rainfall, from floods, coming from the mountains or local floods, or subsurface flow like you see in here. So deciphering this into what is the component, which component of the water is coming from this source, which source, is an important water management question, as well as is this an important hydrology question. Some hydrologic model, for instance, route all the groundwater in a catchment into the rivers, into the river courses, and route it out of the catchment. But in some cases, these groundwaters may discharge somewhere at farther distance from the site of recharge without ever returning into the streams. So this will have an implication for hydrological models. And then in East Africa and in the mountainous areas, there has been a handful of studies in Ethiopia, in Kenya, Tanzania, in these mountains, the Darfur Mountains, in Agar Mountains, in Central Sahara, Cameroon, Atlas Mountains, and valley aquifers adjoining these mountains to see where the water is coming from. And then I'll show you an example from Ethiopia. This is a block diagram showing Rift Valley in Ethiopia and adjoining mountains. And then if you look the Rift Valley here, in many places you find two distinct types of groundwaters: oxygen 18 deuterium depleted waters and those enriched categories. Same here, same there. Different geographies, two distinct categories of groundwaters underlying the Rift Valley. The same in Ethiopia, same in Kenya, etc. So where is this depleted groundwater coming from? So the rapid interpretation without having other data sources is that this depleted groundwater could come from the mountains. So contribution of the mountain block, a subsurface inflow into the Rift Valley environment could explain the presence of this depleted, oxygen 18 and deuterium depleted groundwaters. And then we don't have other constraints like temperature indicators or paleo temperature indicators or other tracers to confirm this hypothesis. But the stable isotopes are telling us, mountains may be contributing to this. And finally, about surface water groundwater interaction, use of these isotopes to characterize the connection between surface waters and groundwaters. And there are also a handful of studies, particularly in the eastern and southern part of Africa, where we have a number of lakes and stream discharge in the Nile. There are a number of studies there. And one of the questions is, for instance, what is the role of infrastructure development? Has infrastructure development such as damming, construction of large reservoirs affected the direction of surface water groundwater relations? And the other question is, what is the role of these streams and rivers in recharging adjacent aquifers? And then one of the classical studies of using isotopes in identifying surface water groundwater connections has been done in Sudan here. So in Sudan, we have two main sources of river water. One is the Nile, the white Nile coming from Lake Victoria, and the blue Nile coming from the Ethiopian highlands. Okay, and the two meets here. And the white Nile waters are oxygen 18 and deuterium enriched because of evaporation in the lake and evaporation in the Sud swamp in Sudan. So these waters are isotopically enriched, but the waters coming from the Ethiopian highlands are not as enriched. And then at the confluence region here, we have several forms of aquifers, and then detection of which water contributes to the recharge has been done based on stable isotopes of water, oxygen 18 and deuterium. But the figure shown here is the use of tritium. Tritium has been used to detect, for instance, how far into the aquifers laterally tritium containing groundwater reached in this part of the region. And then as you go away from the river, because modern waters, river waters contain some tritium, but mind you, we said in this region we have paleo groundwaters free of tritium. So as you go away from the river, the tritium content decreases. And after 4 kilometers, a measurement done in 1976, after 4 kilometers, the tritium level goes back to background values. So this zone, so the Nile water penetrated up to 4 kilometers over a period of 20 years or 15 years. And then that has been used as a basis for determining the groundwater flow velocity in this environment. And this one shows the role of for instance, Aswan Dam here. The Aswan Dam built in Egypt. This is the biggest dam in the region in Africa, Egypt and Sudan. And prior to the construction of the Aswan Dam, the oxygen 18 deuterium plot of waters of the Nile before the construction of the dam shows these characteristics here, relatively depleted. And waters recharged from the Nile water are these characteristics here, the blue dots. But waters which are recharged, groundwaters which are recharged in the Nile Valley after the construction of the dam plot somewhere here in the enriched end of this. So this enrichment is partly because of the reservoir and because of the introduction of irrigation. So other properties of the water, so the stable isotope property of the water in the Nile Valley has changed because of the construction of the dam. And then other properties also change, like salinity and other chemical constituents of the water changes. And then we will know the reason. What is the reason for this chemical and water quality changes in the Nile Valley? And this is a similar sort of plot in the Delta environment here by Gamal 2018, showing 3 components of the recharge water recharging the aquifers: irrigation return water, modern Nile water, and old Nile water, and the groundwaters in the Nile Delta environment coming from mixture of these 3 sources. So the other applications, 2 final slides, is more an in-depth studies like mixing between aquifers. I've talked about this large sedimentary basin aquifers in Northern Africa, and this is not just one unit, one layer of aquifer. These are multi-layered aquifers. Some zones are fresh, other zones are saline. And then, for instance, a study by Trablesi in Tunisia shows that what we call the continental intercalayer aquifer, which is the most extensive aquifer in the region, containing mostly sandstones and fresh groundwaters, vertically leaking. So this has very depleted oxygen 18 and deuterium isotopic content because of its old age. And this water leaking into the shallow aquifer called the Jifara aquifer. So if you sample the Jifara aquifer, you get a mixture of modern day recharge coming from the small rains of the present day in the region, and the vertical leakage coming from the deeper sources. So interaction between multiple layers of aquifers, given that they have distinct isotopic compositions, has been possible, and this has been showed in many places in Africa. And finally, this is my final slide. The contribution of stable isotopes is in uncovering the origin of waters in the geothermal systems underlying the East African region. In the East African region, we have this Rift Valley, the Great East African Rift Valley, extending from Eritrea, Ethiopia, down to Mozambique. And then there are a number of geothermal waters, geothermal groundwaters, manifestations, and geothermal fields. And the question there is a number of geothermal questions, like what is the reservoir temperature, and where is the water coming from, and what is the thermal maturity like. So stable isotopes, for instance, show thermal maturity in some way. This plot is for this region in Ethiopia, and you see these geothermal waters floating on this horizontal axis called the positive oxygen shift. And you have positive oxygen shift at when the reservoir temperature is high, and also when the rock to water ratio, water to rock ratio is low. So you have this geothermal oxygen shift because of the geothermal exchange of oxygen in silicates or oxygen in carbonates with oxygen in water. And then vertical profiles of oxygen 18 and deuterium in geothermal fields in Kenya. This is a work by Darling. I've just taken a small figure from Darling 1996. Vertical profile in oxygen 18 and deuterium in thermal wells, on a thermal well, showing, for instance, lateral inflows. Okay, lateral inflows of water discharging into the borehole, into the geothermal well. So the geothermal well gets its water from multiple aquifers and indirectly indicating geothermal aquifer permeabilities. So there are a number of such examples, whereby isotopes have contributed to our understanding of the groundwater systems, the recharge mechanisms, recharge rates, origin of water, surface water, groundwater interaction. So this is, more or less, grosso modo, what I could say about isotope contributions in unraveling the groundwater resources in Africa. But the literature is widely available out there for further understanding. And thank you very much. Back to you, Didier.
Thank you, Seifu, for your nice presentation. It's a very comprehensive panel about what stable isotope, how stable isotope has contributed for the groundwater knowledge in Africa. Thank you very much for this, your nice presentation. So following this session, I would like to introduce Mr. Bryant Jurgens, probably, I hope say your name correctly. The theme of his talk is susceptibility of groundwater used for public drinking water supply in the United States. Bryant is a research hydrologist with the US Geological Survey in the United States, and he uses trace sensor-based age dating methods to understand contaminant trends in groundwater and to assess the sustainability of aquifers at the state and national scale. I would like to remind the audience that the question may be sent by our app, please download it, or directly on our YouTube channel. This session has simultaneous translations into Portuguese, also in YouTube. Please make sure your direct question to one of our guests. Bryant, your turn, please.
Okay, thank you, Didier. Can you see my screen?
Yeah.
Okay, thank you very much. Again, my name is Bryant Jurgens. I'm actually in Sacramento, California in the United States, and I'm going to be talking about the susceptibility of groundwater use for public drinking water supply in the US. I just wanted to quickly acknowledge the long list of my cohorts here in the US who helped contribute to this work. So I've been part of this national program that has been sampling over 1,300 public supply wells and springs since about 2013. These wells are spread out across the country in 23 principal aquifers that together supply about 90% of the groundwater used for public supply. We've grouped them into classes of aquifers based on their sort of lithology and type and climatic variability. It's important to know that in the United States that we have kind of a different climatic regime east to west. So in the eastern half of the country, it's quite humid, and in the western half of the country, it's quite arid. And so we've grouped these up into different classes of aquifers. We have western unconsolidated aquifers, which are essentially these alluvial basins in arid environments. In contrast, we have these coastal aquifers of the eastern and southeastern United States, which are semi-consolidated to consolidated alluvial plain aquifers that grade towards the ocean, and they're kind of multi-layered aquifers. We have the glacial aquifer, which is in the northern part of the United States that spans east to west in orange. The interior sandstone aquifers, the Cambrian Ordovician, which lies beneath the glacial aquifer, the Colorado Plateau, and the Edwards Trinity aquifer. These are sandstone aquifers of fairly old sediments. We have a couple of hard rock areas. So we have the Piedmont and Blue Ridge crystalline rock aquifer in the east, and the Columbia Plateau basaltic rock and basin fill aquifers in the west. And we have a series of 6 carbonate aquifers sort of spread throughout the country in the southeast and the mid-continent. And at all these wells, we collected tritium, noble gases, and helium isotopes, SF6. We collected CFCs in places where we had potentially terrogenic contamination of SF6. We used the tritium, the helium-3, and the SF6 to constrain the age of modern water, meaning water that was recharged after 1950. We used carbon-14 and radiogenic helium-4 to estimate the age of pre-modern water, or water older than about 1,000 years. And so when we talk about susceptibility, the main thing that we're after is to try and estimate what the age distribution is. We know that when we pull water out of the ground, it's composed of many parcels of water that entered the aquifer at different points of the system and at different times, and all traveled to the well and arrived at the same time. And so if you could unravel that, those package of water molecules, you would see that there's a distribution of age. And so we typically, some of the important features of the age distribution is that we most commonly are interested in is the mean age, but the age distribution can take different forms. In its simplest, up in this upper right hand corner, it sort of shows where there's this area of recharge, and water may travel as a packet towards a well and have some sort of dispersion that takes place. And so you may end up with just a single distribution of age, or a unimodal distribution, either here represented in this blue line with that maybe 25 years, or maybe it took 150 years to reach that well, which would be represented by this yellow line. In other cases, we actually see that we get these mixtures of modern and pre-modern water. So we see a dilution in the tracer concentrations. And so we can sort of model those as sort of a binary mixture. And the lower right-hand corner sort of shows that sort of an example of where this can occur. And Dr. Seifu Kebede was talking about this, I believe, in Africa, where you have an unconfined aquifer sitting on top of a confined aquifer. And so you're getting young water from the unconfined aquifer and really old water from the confined aquifer. And so what will happen is you'll end up with this sort of bimodal distribution where you'll have an age associated with the young fraction and age associated with the old fraction. And then we can estimate what the fraction of modern water is. And that's another metric that's important to us, because the fraction of maybe 1950-year-old water will tell us what the potential for anthropogenic contaminants to be in the well. I mean, it's important too to realize that the mean age is a calculated value of all these different variables. In the most complicated form, it's using this binary mixture, be the travel time through the unsaturated zone plus the age of the modern fraction times the fraction of modern water plus the age of the pre-modern fraction times its fraction. And so what's interesting about this, though, is that this green distribution, this bimodal distribution, has the same mean age as this yellow distribution. So you can see that the mean age isn't always a good indicator of the susceptibility of water to contamination, because clearly this bimodal distribution with 25% modern water is going to behave differently than a unimodal mixture of the same age. So unfortunately, we don't often know the age distribution. We must estimate it using these tracers that have some sort of environmental record, transient environmental record through time, or has a known decay rate. So we typically collect samples at a well, and we have to essentially estimate the age distribution inversely. So we try an age distribution that may correspond to some aquifer type with some known properties. We then have an estimate of how the tracers are moving through that and the sampled portion of the well, and we can calculate what the mixture of tracers is for that particular well. And we compare that with what we measured, and if they're different, then we refine our age distribution until the age distribution gives us some sort of plausible estimate of the measured tracer concentrations that we have. And so we did this for all of these samples. It was quite an effort, and we had to develop strategies to systematically model these ages in some sort of consistent fashion so that they are comparable. And so we tried to simplify things as where we could. We were able to identify samples that are really just sort of unimodal mixtures or single mixtures of age. And then we had these more complicated forms of binary mixtures and that were sort of dependent on the hydrogeology of the system. So in hard rock areas or in fracture flow areas, we often can see these bimodal mixtures between modern and modern water. So we may have a mixture of 10-year-old water with 30-year-old water. But more commonly, we see this binary mixture being a mixture between modern water and pre-modern water. And so we use the dispersion model because it's physically based and can be used to represent a wide range of aquifer types. It does have a parameter that describes the degree of mixing. So lower values of the dispersion parameter would indicate more sort of piston flow behavior or no mixing, and larger values would indicate greater amounts of mixing. In the Western aquifers, we have, it's more arid, and we have sometimes thick unsaturated zones, and we know that travel time through the unsaturated zone can affect the age of groundwater and affects the tracers. And so we've identified or come up with ways to identify those samples and estimate the travel time through the unsaturated zone through tritium and helium-3, because helium-3 is preferentially lost during travel through the unsaturated zone. So after doing this analysis for over 1,300 wells, we find that about 30% of the wells have ages of less than 100 years. 14% of those have ages less than 25 years. But more than 33% have ages more than 10,000 years. The median mean age of all the groundwater that we sampled was 2,500 years, which means that more than half of the samples, more than half the wells have groundwater older than 1,000 years. So people are drinking a lot of very old groundwater in the United States. Some surprising results that we find that age is sort of more related to the aquifer type and its well position than to aridity. We see a number of the eastern aquifers show up red here, meaning that the ages are greater than 10,000 years. This is a very arid environment with high rates of rainfall, but yet we have very old groundwater. In contrast, though, we see in the mountain regions here, the Piedmont and Blue Ridge crystalline rock aquifers, we see much younger water because there's shallower hard rock systems. So flow is going to move through these systems fast. There's high rates of rainfall. So it's not unexpected that we would see younger water in these systems. But the amount of old groundwater that people drink was a bit surprising, or maybe not surprising, because these are public supply wells and they're constructed to withdraw large volumes of water out of the ground. So they're typically constructed at deeper depths and have longer screens. So we see that 75% of the wells are deeper than 70 meters. We can group all of our ages into our aquifer classes and to sort of identify which types of aquifers are older or younger. We find that the coastal and interior sandstone aquifers, that would be these purple samples and these blue samples here, have more than 80% of the samples are older than 100 years. In contrast, this maybe not so surprising, the carbonates, which are here in blue, the igneous and metamorphic rock. So these are fracture flow aquifers, and the glacial sediments, which are fairly shallow systems, have the youngest groundwater ages. But recall that the mean age is skewed towards older ages. If you have 90% of, say, 10-year-old water and 10% of 1,000-year-old water, the mean age is 110 years old. And so that kind of gives these mean ages can give sort of a skewed view of the composition of the ages that are extracted from these wells. And so we can look at these mixtures throughout the country. So these are bimodal mixtures of modern and pre-modern water. We've, for samples that have more than 95% modern water are in blue. So these by and large behave like purely modern water. And in green are these bimodal distributions where we have a significant component of modern water and a significant component of pre-modern water, and these are in green. And then in yellow are samples where there really is very little to no modern water present. And we find that the confined aquifers, which would be representative again as these coastal aquifers, these are deep buried aquifers, tend to be devoid of modern water, whereas these unconfined aquifers of the West frequently have compositions with modern and pre-modern water. You can again sort of look at an empirical cumulative distribution of these samples and their aquifer classes shown here on the left, the fraction of modern water. So anything at 0 is going to be completely pre-modern. Anything at 1 is going to be completely modern. So water wholly recharged after 1950. And anything in between is going to be some sort of mixture between the two. And when we look at the Western unconsolidated aquifers, we see about 50% of the samples have some mixture between modern and pre-modern water. And again, these are sort of unconfined aquifers, and a lot of them have been sort of human altered, or the recharge has been altered by humans because of farming or because of managed aquifer recharge. So in the Central Valley where I'm located, the High Plains Aquifer, which is in the middle of the country, are both intensively farmed. The California coastal basins has been doing managed aquifer recharge since the 1930s. And so these systems, we frequently see wells with these mixtures of modern and pre-modern water that sort of represent two different regimes, a natural regime and now an altered regime. Contrast that again to the coastal where only 10% are mixed. So if we strictly just want to unpack this a little more and look at just the ages of modern groundwater, we do see some differences by the aquifer class. Again, the carbonate aquifers and the glacial aquifer have the youngest ages of modern water. So the glacial aquifer is again very shallow, carbonates fracture flow, and has high rates of recharge, so water is moving very fast. Contrast that with the Western alluvial aquifers, and flow through porous media can be slower than fracture flow. And a lot of these wells, these are deep alluvial basins, they construct these wells at some depth below the water table. And so there's some travel time delay between the recharge at the water table and the travel to the top of the well screen. So it's not too unexpected that we see older ages in these Western alluvial aquifers. The pre-modern groundwater ages largely reflect the mean ages that we said because they're skewed towards that way. I won't spend a lot of time on this, but to say that the Cambrian Ordovician is kind of unique because 10% of the water is greater than 100,000 years. And so these would be a good candidate to sample for Krypton 81 in a number of these areas. The Western aquifers and the igneous metamorphic rock tends to have younger ages of pre-modern water than the others. Again, as I mentioned earlier, that we assessed travel time delays through the unsaturated zone in the western part of the United States, and about 36% of the modern water has some travel time delay. We see that about 18% of the samples are more than 10 years. And so the unsaturated zone is often sort of neglected, either in groundwater modeling exercises or in a lot of tracer studies. And so this shows that the travel through the unsaturated zone can actually be a big contributor to the age of groundwater. And so we've grouped our samples according to these aquifer classes. And of course, there's definitely variability among the different aquifers that make up those classes. And the carbonate aquifers of the US really sort of exemplify this. There's a huge range in variability, and we can sort of, based on the aggregation of all the individual age distributions, we can sort of come up with these characteristic age distributions for the aquifers and compare them for each of the aquifers. And again, here climate and its depth has a large impact on its behavior. This top blue line is the Biscayne aquifer. It's in southeast Florida with high rates of rainfall, and it's a very shallow system. And so this system tends to have the youngest groundwater ages. You could contrast that with the Floridan, which is nearby, and the Ozarks carbonate aquifers, which is in the middle of the continent. These are confined aquifers and are much deeper in the system. And so they have a larger component of old groundwater. The other thing I wanted to sort of point out in this are these plateaus that occur that can, our design is made up so that we try and sample the aquifers evenly spatially, so that we get representatives of wells in the unconfined portion or in the recharge area with confined portions or areas down gradient. And so what happens is you can have populations of wells in the unconfined part of the system that is much younger than the ages in the older confined part of the system. And when you sort of aggregate those, you end up with these two distinct populations with this bridge in between them. But the other thing that can happen is that we have this, it can be an artifact of actually our groundwater age modeling of this binary mixture. Carbon-14 isn't a very good indicator of water between 100 years and 1,000 years. And so some of this could be representative of this age dating gap that we aren't able to resolve without an additional tracer. And so we can take these distributions and sort of compare them across all the different aquifers, and we can calculate this susceptibility index, which is sort of a better measure than the mean age. As I mentioned, the mean age can be misleading when you have these binary mixtures, because you can have a well with the same mean age, but they can behave very differently to land surface contamination. So we developed this susceptibility index, which was published earlier this year by John Sauter. And it's really just sort of a measure of how similar a distribution is to water that is of 1 year old. And so the more similar it is, the susceptibility index is going to be higher, and the more dissimilar it is, it's going to be closer to zero. So really old water is going to be closer to zero, and very young water is going to be closer to 1. And when we use this index for our characteristic aquifer age distributions, we can sort of separate out which aquifers are susceptible to land surface contamination. And by and large, as groups, we see that the carbonates and the igneous and metamorphic rock aquifers are the most susceptible to land surface contamination, which isn't surprising because these are fracture flow systems, and so water can move much more quickly and then through porous media. On the other end of the spectrum, we have the coastal and the interior sandstone aquifers, which isn't, also isn't surprising, but this index can also be sort of used in a reverse fashion, that a lot of these aquifers, even though that they are protected and from land surface contamination, there's geogenic contaminants that often are associated with long time frames. So in these aquifers, things like radium and trace elements and redox biogeochemical transformations can increase some geogenic contaminants in the groundwater. So while this ranking is for surface contamination, it doesn't mean that there's not issues related to their drinking water quality. So in doing this, we found that our groundwater age modeling is most successful when we have multiple tracers. There are a number of issues with the tracers where we have helium-3 confinement, we can have terrogenic SF6 contamination, and so it's really important to have as many tracers at a well as possible in order to figure out what the age is of young water and of older water. And so we're really hopeful that Dr. Liu and his group can make the sampling of argon-39 and krypton-85 more cost-effective and easier to sample for in the future. And again, that some of these samples, individually, there may be a large degree of uncertainty, but collectively, they make a lot of sense in terms of how we think the systems will behave. But going forward, though, it's important that we resample these wells for tracers, because we can refine our age interpretations through repeat sampling, and we can also test the other hypothesis, which I didn't go into, that these models sort of assume that the systems are at steady state, and by sampling for the tracers through time, we will be able to tell whether or not the aquifers are being managed in a sustainable way. So in conclusion, I think I was most surprised by doing this, by seeing that we drink a lot of old groundwater, that this system really, this study sort of really reinforces our understanding of these systems and its relation to age, which are driven by these recharge and its flow system characteristics. I'll close with a shameless plug. I have some software that sort of enabled this analysis that is freely available to people if they want to go to my GitHub site. This is DG Meta, which is dissolved gas modeling and environmental tracer analysis. And then the modeling component is done by Tracer LPM. We have a second version of this on my GitHub site. Anyway, so thank you very much.
Thank you, Bryant. Excellent talk. I guess we have a lot of subject for discussion after the next presentation. Now I would like to introduce Professor Liu. He will talk about radiokrypton and radioargon dating from 1 to 1 million years. Dr. Liu is professor of physics and dean of the School of Gifted Young at the University of Science and Technology of China. He received his bachelor from USTS in 1987 and PhD from Berkeley in 1994. And through his career, Liu has been developing techniques of laser manipulation and laser spectroscopy of atoms, and applying these techniques to ultrasensitive trace analysis, studying nuclear structures and testing fundamental symmetries. He currently serves on the advisory boards of the Max Planck Institute for Nuclear Physics in Germany, the National Institute of Metrology in China, and the National Laboratory of Physical Science at the microscale in China. I would like to remind our audience that questions may be sent by our APP or directly on YouTube channel. The session also has simultaneous translations into Portuguese, also on YouTube channel. You can choose your preference, language of preference. And please, when you send your question, please make sure that send directly your question to one of our guests. Thank you, Professor Lu, for your acceptance in participate in this session. Please, your turn.
Thank you, Dr. Didier Gastmans. And so I would like to share my screen. Can you see my screen now?
Yeah.
Okay. And I would also like to thank the previous two speakers for two very nice talks and on the introduction of tracers and water ages. So I'm a physicist, and I want to tell you what we do in collaboration with hydrologists worldwide. So these are my colleagues in Hefei. The city is about 450 kilometers west of Shanghai. And we formed a laser laboratory for trace analysis and precision measurement. And at the bottom, you see our laboratory website. And also we are supported by the Chinese National Science Foundation, the Ministry of Science and Technology, and by the Chinese Academy of Sciences. So the principle of radioisotope dating is straightforward. Krypton-81 is an isotope. It's produced by cosmic rays in the atmosphere. And since it's a gas, once it's produced, it stays in the atmosphere and gets mixed very uniformly over the entire Earth's atmosphere. Whether you take a sample in Brazil or in China or in the US or in Africa, we have actually measured air samples from all over the world. The isotopic abundance of Krypton-81 are the same. It's a constant. We call it I0. And in the atmosphere, it's continuously being produced and also continuously decay. It has a half-life of 227,000 years. Surface water exchanges krypton with the air, so it also acquires the same isotopic abundance I0. But as soon as the water goes underground, it's cut off from the atmosphere. There's no longer fresh Krypton-81 coming in. And so the isotopic abundance of Krypton-81 decreases over time due to radioactive decay. And so by measuring, by drawing water and measuring its isotopic abundance, one can figure out the age of this water body. Water itself has no age. It's just a molecule, but we define the age of this water body by how long this water body has been separated from air. So that's what we call the age of groundwater. And it's very useful information because hydrologists such as Bryant and Seifu and Didier, they can go out and from the ages, they can figure out the flow and the flow path, flow speed. And so this is a very useful information for example, groundwater management. So such work has been done, as in Bryant's talk you heard, with carbon-14. Now, carbon-14 is like krypton-81. It's also produced in the atmosphere, and it oxidizes into CO2. This is a very fortunate step because carbon itself is not a gas, but CO2 is, and it stays in the atmosphere and gets mixed really well. This is a radioactive decay curve of carbon-14. When the sample age is much less than its half-life, this part of the decay curve is flat, so it's not very sensitive. And on the right side, the curve is quite steep. The sensitivity is high, but then there is another problem. In nature and also in the laboratory, you always have a little bit of modern carbon mixed in with the sample. For example, if you have 1% of modern carbon contamination, then when you go measure carbon-14, you get 1%. And that corresponds to an age of 30 or 40,000 years. And that's one reason why there are so many places where the carbon-14 age is 30 or 40,000 years. Nowadays, we go measuring the age with krypton-81. We found the ages are actually 10 times or even longer. It could be 1 million years old. And that, I think the reason is because the sample will always have a little bit of modern carbon mixed in. And so that prevents the radiocarbon dating from dating really old water. So around its half-life, an isotope has an effective dating range. So this is the effective dating range of carbon-14. If you want to go beyond or below this age range, you would need isotopes of different half-lives. And very fortunately, in the atmosphere, we have 3 other gaseous radioactive isotopes of and their half-lives fall into different orders of magnitude. So then the effective dating range linked together, going from a few years all the way to, we can go to 1.3 million years now. So if you're interested in young water below 50 years, krypton-85 is a suitable candidate. And if you're interested in the range of 50 to 1600 years, then argon-39 is suitable. And if you go, if you're interested in 20,000 and beyond, all the way to 1.3 million years, then krypton-81 is a good isotope to use. I used to say 40,000 years, but now the precision of our measurement has improved. Now we're pushing this one down to 20,000 years. And actually at 20,000 years, it kind of overlaps with carbon-14. So I'm actually very interested in doing a comparison between a carbon-14 age and krypton-81 age. So if a hydrologist who are interested in doing such a comparison, please let me know. I would like to collaborate, and I think it will be very interesting to do these comparison. And in the future, we want to push it down further, perhaps down to 10,000 years with krypton-81. So the noble gas isotopes are nice because they don't chemically react with things in the environment. So they are ideal isotopes for dating and tracing. I said gaseous isotope is important. This is one example of a non-gaseous isotope, chlorine-36, that has been used for the long old water. It's not a gaseous isotope, so once it's produced, it falls quickly to the ground. As a result, the initial distribution, initial isotopic abundance of chlorine-36 is not uniform. Over the continent of the United States, the initial concentration of chlorine-36 can be 1,200, and then towards the coastline, it can be 50. So And this is determined by some weather patterns that could change from certain age to another age. That's the reason that when you get a chlorine-36 analysis, you would have to model some initial value in order to determine its age. And that has been the difficulty with chlorine-36 dating. And with gaseous isotopes such as krypton and argon, then the distribution is uniform. So that's the advantage for gaseous isotope. These advantages were pointed out long ago in the 60s by Hans Oeschger and Ugo Loosli at the University of Bern. But at the time, it was just very difficult or even impossible to measure these isotopes. The isotopic abundance is quite low. For krypton-85, it's 10 to the minus 11, argon-39, 10 to the minus 16, and krypton-81 is 10 to the minus 13. So these are much below the detection limit of mass spectrometry. We had to come up with a new way to measure rare isotopes. And this is, we call this method atom trap trace analysis. So here atoms coming in, the gas isotopes, they come in through this tube into a vacuum system as individual atoms. And these are neutral atoms. They are not ionized, not like in the mass spectrometry, whether you deal with ions. We deal with neutral atoms. Okay, and then we send laser light from the side to collimate the atomic beam, and we have this laser we shine head on and to slow the atoms down. And then once the atoms are sufficiently slow, we send in 6 laser beams over here to capture the atoms. The atom in the trap glows because there are 6 laser beams shining on it. So it appears as a bright dot, and modern cameras has no problem seeing the glow of a single atom. So here's a very clear signal of a single krypton-81 atom. So that's how we count the number of krypton-81 atoms in the sample. This is the actual setup, and it's about 3 meters long, and laser table is on the side. This is a vacuum system, and this is a camera that's looking into the vacuum chamber to see that bright spot in the middle of the vacuum chamber. So here are the results. When we measure krypton-81, we always measure a stable isotope like krypton-83 almost simultaneously. So we measure the ratio instead of the absolute counting rate. A ratio is much more stable than the counting rate itself. In this case, we demonstrate that counting rate can vary for one sample, but the ratio between krypton-81 and krypton-83 are always the same. So that makes a reliable measurement. We also test ourselves by asking our friend and colleague, Roland Perchard at the University of Bern, to give us tests. He can mix krypton-85 of different isotopic abundances and then send it to us to see whether we get it right. In fact, every collaborator can test us. This is what you do. Say when you send us 10 samples, one of them, don't send us all of the sample. You can keep half of them for the next time, okay? So the next time you can send us a new batch of 10 samples, but this, with this repeat sample hidden within the batch. And then you can see whether we give you the same value as the last measurement. So that's one way for our collaborator to test us. So we've done all of these things. And so this is the procedure for radiokrypton dating. First, you go to the well and you extract the gas. You don't need to bring back water. You just need to bring back the gas. That makes it a little bit easier. Okay, so the gas extraction part is we use a specialized device that it's something that you can carry with one person and has a few knobs on it. The key is to get the water sample before the water touches modern air. And so we don't want modern air mixed in the gas sample, because if you have modern air, the age will be 0. So this is a gas extracted from the water, and it's put into a compressed cylinder, and this is sent to our laboratory. We then use chemical and physical method to purify the krypton or argon from the raw gas. Okay, so from 1 liter of raw gas, we get about 1 microliter of krypton. Then we leak this 1 microliter of krypton into our atom trap vacuum system, and we count for atoms. And once the atom counts and the ratios are measured, you can use this formula to calculate the krypton age of the water. Okay, so this first step performed by our collaborators worldwide. And if you're doing this for the first time, you need a friend and colleagues who are experienced to help you. But once you have done it once or twice, you become comfortable with this, and you'll be able to do it on your own. So these are what our machines can do today. So these are precision, age precision levels, and it depends on sample size and sample age. Obviously, if you send us more samples, we can do a better job, more precise measurement. And it also depends on sample age. If the age is too short or too long, then the precision drops. Okay, so that's for krypton 81. We usually ask for 1 microliter of krypton, which can be extracted from about 20 kilograms of water. For argon 39, we ask for 1 milliliter of argon, which can be extracted from about 2 kilograms of water. So 20 kilograms of water for krypton 81, 2 kilograms of water for argon 39. And I think krypton 85 is somewhere in between these two. So we have been collaborating with colleagues worldwide. I think Dr. Kebede talked about the Nubian aquifer, the intercalare aquifer. We've done some of them. And we also collaborated with Dr. Gastmans in the Guarani aquifer. And we also worked with our US colleagues over here. And so all the papers are listed under this website. You can Google ATA primer. That's the Atom Trap Trace Analysis primer. You get to our website. There are all the papers listed, and also all the colleagues, the experts listed there as well. For example, if you want to go to the field to extract groundwater, you don't know how to do it, go to our website, find out who near you knows how to do it, and then hopefully you can collaborate. So let me just give you a few examples. And this was a collaboration we did with IAEA. I think Dr. Gastmans was on the team. We dated some water from the Guarani aquifer and from the krypton 81 age, and also from the helium-4 content in the water. One can figure out the flow of the water, the age of the water, and surprisingly for me, it was figured out that groundwater flow has been a major carrier of helium from deep underneath to the atmosphere. So that's why the title of this paper is Continental Degassing of Helium by Superficial Discharge of Deep Groundwater. So it was very interesting work. This is a more recent work, and it's led by my friend at University of Chicago, Reika Yokochi. And this is a study of the Negev Desert in Israel, and from the krypton 81 measurement, and from the stable isotope analysis, like what Dr. Seifu Kebede did, the D-axis, one can figure out that it actually was discovered by Reka, that the samples we have can be explained simply by the mixture of two end members, one over here, one over there. And so from this, so that's why the title of this paper is Radiokrypton Unveils Dual Moisture Sources of a Deep Desert Aquifer. And so, so I'm very proud of this. This made the cover of the Proceedings of the National Academy of Sciences. I'm proud for two reasons. One is that we got the groundwater source tracing, radiokrypton on the cover. The other reason is that I actually took this photo myself. So I found it, I feel really good that the photo I took made the cover of the magazine. Yeah. And there's other reasons to date water. And this is a place where China is exploring to establish a nuclear waste repository. And so when you want to establish nuclear waste repository, you want the water there to be really, really old, so it barely flows. So we've done this work. So Krypton 81 dating is a good measure to assess its suitability. So we've done this work for the US, for China, and also for Japan, and we'll be glad to do this for other countries as well. There's a collaboration set up by IAEA on dating very old groundwater using Krypton 81 and other tracers. And so far, IAEA has selected 12 countries, 13 countries, and so we are doing it right now, and hopefully we can work with more countries in the near future. And there might be other new ideas. People talked about CO2 sequestration site that could be using Krypton 81 dating to help assess its suitability. People talked about volcanic released gases, hydrothermal vents, and we hope to have more experts from different fields to tell us new ideas. We would very much like to collaborate with you on testing new ideas. And this is just the groundwater, and I will not talk about, but we are certainly working on, collaborating with oceanographers for mapping ocean currents and also dating ice in Antarctica, in Greenland, and in the Tibetan Plateau, many mountain glaciers as well. So I stop here. Thank you very much.
Thank you, Dr. Lu. Nice presentation. I'm very impressed with the actual amount of water you need to determine Krypton 81 and argon 39 concentrations. I remember the first samples we sent to argon was about 30 liters, yeah, 30 liters of gas. And now you are able to determine in 2 liters of water. This is amazing. I have some questions of the audience, and I guess I will start my questions. They're personal questions, and I would like to start with Dr. Seifu. There are two questions regarding the difficulties to work or to establish collaboration and work with stable isotopes in Africa, and also how large and effective is the group network in Africa, and who runs the GNIP network, how it works, and one question about lab capabilities in Africa for isotope analysis. We know that we have the IAEA spreads many or installed many labs able to run stable isotopes determination in Africa, but some of them are not working very, very well. I would like to know from Dr. Seifu his impression about that.
Yes, thank you very much, Didier, for the very interesting questions. You know, I would classify the last, let's say, 60 years into two periods. So the first period is between 1961 and 2008, and then post 2008. So in terms of isotope capabilities, isotope measurement capabilities in Africa, before 2008, there may be one or two laboratories capable of measuring stable isotopes of water. Because, you know, prior to that time, the machines that were utilized are mass spectrometry. But after the introduction of the laser spectroscopy in 2008, then a new phenomena came because of the ease of measuring these isotopes. And I would say initially we anticipated that it was much easier. The machines can be used everywhere by everybody, etc. So a number of these isotope measuring machine, laser spectroscopy machines have been distributed in many laboratories in Africa. I can mention countries' name, but nevertheless, very few of them are running currently. The problem is not with the machines, and the problem is not with the equipment itself. It is more of the capacity, integration of isotopes in water resources management practices. You know, you can measure, but there is no other entity or other body who is interested in your samples or in your analysis. So we need to enhance the capacity of use of isotope data along with the capacity to measure this data. And there are some successful countries whereby any water exploration, groundwater exploration activities incorporate isotope hydrology as part of tools like geophysics, like remote sensing, like geochemistry or water point inventory pumping test, but not everywhere. In Ethiopia, for instance, government projects that invest on groundwater exploration and development require consulting companies to do isotope measurement. So there are a number of requests, and the laboratories keep running regularly. So yeah, the ease of measurement is there, out there, but not everywhere successful measurement has been conducted so far. But there are some good cases that can be mentioned, like in Ghana, in Tunisia, in Morocco, in Ethiopia, Egypt, South Africa. There are a number of laboratories running the laser-based isotope machines. And with regard to the second question was about the collaboration.
Yeah, about
possibilities
GNIP.
of collaboration.
About the
GNIP,
global
yeah.
network,
GNIP,
GNIP, yeah.
GNIP is run by IAEA, and initial IAEA and the World Meteorological Organization when it was established, and most of these GNIP stations are, the sampling is done by government agencies, meteorology agencies, and shipped to the IAEA for measurement. And so you don't pay for it, and the IAA covers the services, the shipment, and the analysis. And yeah, that is how it is being run currently. But there are some short-lived stations that are serving projects. Okay, and in some cases, these short-lived water sampling stations are also integrated into the GNIP stations by discussions and collaborations with the IAEA.
Thank you, Seifu, for your answers. And moving to...
But finally, sorry, Didier.
No, go ahead.
I would say, with respect to what oxygen-18 and deuterium isotopes can tell us, they tell us half of the stories, and most of the stories remain out there. What is the mean residence time of the water? Where is the recharge coming from? What is the recharge rate? All these require additional traces. We need either international collaborations or more miniaturization and easy methods to measure these isotopes, the other isotopes we are talking about, like tritium, carbon-14, and CFCs, etc. Thank you very much.
Thank you for your answers. I guess here in Brazil we have almost the same situation. So we have some equipment installed, but stable isotopes hydrology started to become more how to say this, more popular in the middle of 2005, 2006. But there is no request for this kind of information for groundwater management plans, for example. I guess, as you told, it's very interesting to couple many or other tracers to have an idea about from where the water comes, from where the water flows, and the time of recharge, and etc., etc. I guess a multi-approach is very important. I have a question for Bryant. I have two questions for Bryant. The first one is, let me find here, is about age, groundwater age information. How this information is used in US for groundwater management, and also I have second one is, so in São Paulo we also have a monitoring network of sometimes very old groundwater, but in unconfined aquifers. And also we use water wells, for supplying, as well to monitor the degradation of water quality. What kind of recommendation would you give to us to improve the results of groundwater regional monitoring programs based on these kinds of wells, this public supply wells? Do you?
Sorry, just unmuting. Could you repeat the second one again? Is it about like how to use the information from the public supply wells, because they're
for groundwater management? So age or residence time of groundwater is in some way important to manage the use, and how fast is the replenishment of the aquifer. And this is a point very interesting in Brazil, because as in the US also we use a very, very old groundwater, and how we can use this information for management purposes. And the second one is the lesson about the use of public supply wells for this kind of quality and groundwater age programs?
So I work both with state and national levels, and the state level is much more focused on how we can use this information to sort of better manage our systems. And one of I think the thing that's most often used with the age is to, if you have some idea what the age distribution is, you can kind of reconstruct past trends, and if you're successful at that, you can potentially predict future trends. And so nitrate is probably the most common example. So I've been in study, there's just been a number of studies that have used the age to sort of reconstruct nitrate trends in wells and then make predictions about what nitrate will be in these wells in the future. Right now, one of the things that we're trying to do, I think both nationally and state, is to use this information to try and actually reconstruct the structure of age within the aquifer, because we know that contaminants are related to its age. And if you can reconstruct the age of the entire aquifer, you have some idea what wells are going to be, based on their location, where what wells are going to be impacted by particular contaminants, and how those contaminants are going to move through the system. I know that in the past, public supply wells were not thought of as maybe good candidates to understand age, because they mix so much water in them. But I think, you know, with the models and with tracers, that we can get better ideas about the mixtures. And so we often use, in the most simplest form, if you only have one tracer, whether that be tritium and even carbon-14 to some degree, you can use to assess maybe potentially different fractions of age. You know, most of concern, you know, public supply wells were concerned about anthropogenic contaminants. Carbon-14, you know, it's possible that some of the trace elements are of concern. Once you get past, you know, 10,000 years, you can get you know, trace elements to become an issue, because the pH of groundwater and gets higher. So just sort of my comments on responses to those two comments. Hopefully I answered.
Yeah. Did you consider use carbon-14 for young groundwaters? Because you have a peak of groundwater like tritium since the 60s, and the activity of carbon-14 in atmosphere reach 150, 160% of modern carbon. And did you consider to use this information to that young groundwaters, for example?
Yes, we do, actually. That's one of the things that we've really tried to take advantage of. I know in the past, carbon-14 has often just been used as a tracer of old groundwater, but it actually can provide a lot of information about young groundwater. And, you know, collecting both tritium and carbon-14 together can really help resolve that. You know, the issue with carbon-14 is the potential for its signature to be diluted by dead carbon sources. But we have, surprisingly, we've had more success using carbon-14 to date younger water in siliciclastic systems where we don't have a lot of dead carbon. But even in systems where we do have some dilution, you can potentially resolve the dilution between by looking at relationships between tritium and carbon-14, and we frequently took advantage of that throughout that effort that I presented today in the U.S.
Thank you, Bryant. And now the final question, because we have we over time a little bit for Dr. Lu. I have a final question for him, and this is an interesting question because we know that most of the groundwater that people are drinking has more than 50 or 100 years old. It's about 99% of the water is an important resource, but there is no renew in this this water or in a management time frame time. So what are the perspectives to use Krypton 81 and Argon 39 in a more usual form worldwide?
The use of these isotopes for worldwide use?
Yeah.
So we are actually currently collaborating with hydrologists from all over the world. We are doing that. Actually, our samples, I'm very proud of this. The samples we receive in Kebede come from all 7 continents. Yeah, so we're doing that. Yeah, and we're building more machines. We now have 6 machines, but the demand is so high, we may add more machines in our laboratory.
This is interesting, but do you think that I guess Professor Dr. Seifu did a comment about how to convince water management people that this information is important. Not only, okay, we are talking in a scientific group and we know how important is this information, but how to make this available information or to make this information important also for water management, water managers around the world.
So that's probably better answered by Bryant or Seifu on water management.
Yeah, I guess this is a good point for we that we are scientists and researchers, but we need to try to translate our knowledge and our information in a better way for management people.
Yeah.
So I would like again to thank all the speakers for the very nice presentation. It's a very interesting overview about the capability of isotopes to tell us something about groundwater. And I would like to ask all the participants and all the audience to follow us, ABBAS, on our social media pages, download the event app and participate on our thematic WhatsApp groups, which are a great place to meet friends, expand your network, and warm up for our presential event in August 2021. And stay tuned that we will release in December, the December attractions soon. Thank you and stay with us. Thank you for the audience, and thank you again for the speakers for the nice presentation. I guess it's very interesting for all the audience. Thank you.
Thank you for having me.